Our second speaker this morning will be Professor David VanDerbilt from Rutgers. He's going to tell us about the modern theory of ferroelectricity. Please.
Okay, thank you. It's a real pleasure to be here. Thanks for the invitation. I was here once before. I had to look back at my notes. It was in 2001, so quite a while ago. I hope to come back 18 years from now, but by then I'm not sure I'll be able to walk up the hill. Anyway, I'll be giving a second lecture about topological insulators, the first lecture about theory of ferroelectrics. And I'm going to start here by discussing the theory of polarization and what is called the modern theory of polarization, which essentially is also sometimes called the very-phase theory of polarization, because, of course, the most prominent feature of a ferroelectric is its electric polarization. And our community, the computational electronic structure community in 1992, we didn't know how to calculate the polarization. We were trying to work on ferroelectrics. That was an obvious problem. And through the joint efforts of several people, Rafael Aresta and our group and others, we cracked the problem and found that there's a formulation of the electric polarization in a way that is rather unfamiliar to most people. So the first part of my talk, I'm going to focus on this theory of electric polarization. The second part, I'm going to talk about something a little different, the so-called effective Hamiltonian approach, which is used to describe ferroelectric phase transitions in, say, perovskite ferroelectrics as a function of temperature. This is a more classical type of approach, but based on first principles calculations. And then, to the extent that I have time, I'd like to talk a little bit about the theory of flexoelectricity. Unfortunately, Gustav didn't talk about flexoelectricity in his talk because he's giving an entire talk about it, I think, tomorrow or Friday, I don't remember. So this will be a little bit out of order. I would have preferred to have the phenomenological talk first, but and then the last part, I have a little flavor of some work we've done in my group recently on looking for novel ferroelectric materials way outside the perovskite family in corundum derivatives. But I mainly want to focus on the first two or topics, and then to the extent that I have time, I'll do 3 and 4. So we'll see how far we get. Okay, so what's the problem with calculating electric polarization? And by the way, stop me with questions at any time, and I will pause for questions after the end of each of the major segments here. Okay, so what's the nature of the problem? The nature of the problem, well, first of all, the context. We do calculations in the context of density functional theory, which is sort of the standard model of computational electronic structure these days. I won't describe it, but you probably know that using these methods, one can calculate energies and forces, and from the forces get relaxed structures and calculate phonons and so on with quite good accuracy. There are standard code packages that implement these things, and this was all true at the beginning of the 1990s. Okay, what's the problem with electric polarization? In textbooks, electric polarization is usually introduced with a picture like this. You have little discrete dipolar entities surrounded by vacuum in a unit cell. There's no charge density at the boundary of the unit cell, and the polarization is the dipole moment of this entity divided by the cell volume. Unfortunately, that's not the way charges come to us in nature. Real materials have the nuclei as point positive charges, but the electrons are distributed in these quantum mechanically distributed charge clouds. This is sort of a contour map, and I've drawn it with some distortion so that you can see in this case there's some polarization to the left or right based on symmetry, but how would you calculate that thing? And this is just to emphasize, this is a contour plot of charge density calculated in the ferroelectric state of lead titanate, and these contours are contours of charge density, and the point is, there's no place in between the atom where the charge density goes to 0. There's no way to draw a unit cell in parts of the unit cell where there's no charge density. And so we have a problem that's more like this. Now I've changed the picture so that the polarization is either in the up or down direction based on the symmetry. And so one idea is you just say, well, I define a unit cell. Within that unit cell, I calculate the dipole moment. So for example, this unit cell, I calculate the dipole moment in this green unit cell by integrating up the charge density like this. And then I divide by the cell volume. and that's going to be my definition of polarization, right? This particular choice of unit cell you see gives a polarization kind of close to 0. But the problem is that if I make different choices of location of the unit cell, I can get very different answers. This one has a lot of negative charge at the bottom, so the polarization is up. This one has a lot of negative charge at the top, so the polarization is down. So I can get any answer. It turns out you can prove that if you average over all possible locations of the unit cell, you always get 0. So this is simply not a useful approach. And after you think carefully about this problem, you come to the conclusion that actually the polarization is not a functional of the charge density. If you know the charge density exactly in the unit cell, that's never enough information to tell you what the electric polarization is. You need some information that goes beyond just the knowledge of the charge density. You need to go deeper and have something that depends upon the quantum mechanical wave functions. Okay, so let's make use of the quantum mechanical wave functions. I think you all know that in a crystalline solid, the wave functions are these block wave functions psi and k. K is a wave vector label, n is a band index. And so, essentially what we want to do when we calculate electric polarization is calculate the expectation value of the position operator. If this were just an atom or a molecule, this would be easy to do because the wave functions decay exponentially when you get outside of the atom or molecule. But block functions run over all space. And actually, here I've done something that I plan to do a little bit later, write things in terms of a self-periodic block function, but don't worry about that. The main point is that this position operator, let's say the x operator, if I plot it versus x, is this red line, which grows without bounds, and then I multiply it times the block function, which is something wavy, and this oscillation gets bigger and bigger and bigger, and I can't integrate that thing. That's not a well-defined integral. If I integrate it over one unit cell, the answer will depend upon where I choose the unit cell boundaries. So this is not useful. The main problem is that the position operator expectation values or matrix elements of the position operator between block functions are not defined. So that's the problem. That's where we were in 1992. Okay, what's the solution? Well, the solution, basically we have to, as I said, go beyond charge density and look at the wave functions. And let me now just do the quick review. Real space crystal looks like this. In reciprocal space, we have wave vector k, and we have some band structure. We have some occupied bands and unoccupied bands. If I look at one of these bands, let's say this occupied band, it's this block function, and the block function takes the form of an envelope function, e to the ikx, times some underlying structure. So the overall block function looks like this. But we can think of this as the envelope function times something which is periodic. It looks like this. This is called the cell periodic block function. So the cell periodic block function is the block function with this e to the ikx factored out. So I pre-multiply by e to the minus ikx. So this uk of x is what we call the cell periodic block function. It's more convenient. So at different wave vectors, uk, this changes shape, but always has the same periodicity. And that will allow us to take derivatives with respect to k of u, whereas derivatives with respect to k of psi are ill-defined. So that's really, I'm jumping ahead a little bit, but that's really the reason we use these cell periodic functions. Now, either the block function or the cell periodic function, its energy I can think of, it's usually drawn this way. This is the one-dimensional Brillouin zone for a crystal of lattice constant A, so the Brillouin zone runs from minus pi over A to pi over A, and you have some energy band. This is the way it's usually drawn in textbooks. But the fact is that this state over here and this state over here are exactly the same state. And sometimes you see this drawn in kind of an extended zone scheme, but again, this label and this label are duplicate labels for exactly the same state. And so another way to think about the Brillouin zone is that it's really a loop, right? In other words, if I identify the left side with the right side and wrap it up into a circle, and then I plot energy as a function of the surface of the cylinder. So I'm plotting the energy on the surface of a cylinder. I'm not sure the perspective is good enough, but anyway, I'm plotting the energy band on the surface of the cylinder because I'm regarding the Brillouin zone as a closed space in one dimension that makes a closed loop. And so once you have a closed space topology can come in and play some kind of role, because you can have some kind of connection as you go around a closed space. Okay, so we'll come back to that in a minute. Here's where we were a moment ago. If you imagine writing the polarization in terms of matrix elements with the position operator, no, that doesn't work. Those are not well defined. In quantum mechanics, we know that we can write momentum as minus I h bar times the gradient with respect to position. And so if I think in terms of the complementarity of position and momentum in quantum mechanics, you can imagine it's plausible that I can write the position operator as I times the gradient with respect to the momentum, or since we're using crystal momentum, the h bar isn't there, so I can maybe replace r by the gradient with respect to k. So this is a very hand-wavy, extremely hand-wavy argument. I replace r by gradient of k. I also have the cell periodic wave functions here instead of the original ones, and this turns out to be the right answer. First of all, it's well defined because the gradient with respect to k of the wave function is well defined, whereas r times the block function is not well defined. But there's some subtleties. This is basically going to turn into a Berry phase, and I have to explain a little bit more about what this is. But this turns out to be the right answer. Okay, here's the derivation, well, outline of the derivation, and I'm leaving out the heart of the derivation, but this is basically how it went. So in, I think it was 1992, Resta wrote a paper which basically carried out this explanation. He said, let's for a moment not think about calculating the polarization of a given crystal in a given situation. Let's imagine that we start with the crystal in some configuration, for example, the centrosymmetric paraelectric structure, and then we slowly move the atoms or make some other slow adiabatic change to the crystal until we get into the final configuration that we want, let's say the ferroelectric structure. And during that process of slow change, I can calculate the rate of change of the polarization. And what that really has to be is the current that's flowing, because in order to arrive at a polarized structure, you have to displace charges. So J of R is the current density in the unit cell. You integrate that over the unit cell. So this is the total amount of current that's flowing. That's the same thing as the rate of change of the polarization. So I use this expression instead of this expression, which is the naive one that we tried to start with. And the problem here was that this kind of integral is not well defined in the periodic system, because r times rho of r is not a periodic function of space. But this current density, J of R, is a periodic function of space, and so it's possible to average it over one unit cell in this way without any ambiguity. And so he said, well, okay, so the change in polarization going from configuration to configuration B along some slow adiabatic path is given by integrating up the rate of change of the polarization times time. And the rate of change of the polarization is something that we did have formulas for at that time. I'm not going to explain to you exactly what those were. It comes from linear response theory, which is like a Kubo formula approach. So it was already possible to calculate derivatives of polarization with respect to, let's say, displacements. But the polarization itself, we had this formula. Okay, so then the question was, if I go from configuration to configuration A to configuration B along some path, suppose I follow some other path, am I guaranteed to get the same answer? And so Kingsmith and I, in 1993, worked out the consequences of this, and to some extent we did it by going back to earlier papers of Fallis, and found that yes, there is a way of writing the change of polarization as something that depends only on the final configuration minus a polarization at the initial configuration where there's some formula for the polarization. So that means it is independent of path, well, almost, with a caveat that I'll come to in a moment. And here's our formula for the polarization that we derived. We basically started with Resta's explicit expression, which I haven't written out, and then did some mathematical tricks to get it written in this form. So what's written here is, this is the sum over occupied bands, the integral over the Barium zone, and then what's here is the cell periodic block function and then the gradient with respect to k operating on that self-periodic block function. Okay, and this is basically the modern theory of polarization, or what's called a Berry phase formulation, because this thing is really a Berry phase, as I'll come to in a moment. Okay, so I've skipped some of the steps. I have to refer you to some of the papers in order to do this. Again, heuristically, the idea is that the x operator can be replaced by id by dk. And when you do that, so here I've simplified to a single band in one dimension. And if I do that in a single band in one dimension, I can rewrite the polarization so these prefactors get simplified in one dimension. It's just minus e over 2 pi. I can write this as phi over 2 pi, where phi is equal to this object. And this object is what's called a Berry phase. So what this is, since I'm in one dimension, this is just a one-dimensional integral over the Riemann zone, but I'm thinking of that as a closed loop. So I go around a closed loop, which is the Riemann zone, so I've written it with this little loop integral to emphasize that, of this uk d by dk uk, and the mathematicians know this as a Berry phase. Yeah, it is a Berry phase. So why do we call it a phase? We call it a phase because this phi can run from 0 to 2 pi, but if it's, let's say, if it's 2.5 times pi, that's really the same as a half pi. It's naturally a phase angle. And so I need a little tutorial on this to explain this.
Do you mind if we interrupt you for a question?
Sure, absolutely.
So in the previous slide, when you move from Resta's formulation to your formulation, so Resta simply, as far as I understand, proposes to integrate over time.
Yes, well, or over.
Time one, whereas your expression, you're integrating over k space, or.
Well, I mean, this also involved an integration over k, and it also involved an integration over time. Or more precisely, what you do is you introduce some parameter lambda, which is, let's say, you're displacing atoms, so that would be the distance that you've displaced the atom. And so let's call the parameter lambda. You can write this as dp d lambda times d lambda. So in a sense, you're integrating over the parameter, but at the same time, you also have to integrate over kx, ky, kz. So this is a 4-dimensional integral. Here, it's just a 3-dimensional. You only have the 3-dimensional integral over k at the beginning and at the final configuration, and the difference between the two. Right. So, I mean, to implement this formula, what you would typically need to do is pick, 4 or 5 points along the path, and then calculate, along the path and do some finite approximation of the integral. And whereas here, all you have to do is do the calculation at the initial and the final configuration. Moreover, if the initial configuration is centrosymmetric, then you already know that the polarization is 0, so you really only have to do the final one, except there's some twists about that. Okay, so let me, I said this is a Berry phase. Let me kind of go to the mathematical side for a moment and say what a Berry phase is mathematically. So you have some complex vector space, and in this complex vector space, there's a complex vector u with a parameter lambda, and lambda is going around some closed loop. And so most of the time in physics, this would be the ground state of some molecule, or it could be the block function, depending upon wave vector k, or it could be some other quantum mechanical wave function. But mathematically, it's more general. Anyway, so usually this is some kind of quantum mechanical wave function, and we carry it around the path. So at each lambda, the Hamiltonian is a little bit different, but when we come back to here, the final Hamiltonian, of which this is the eigenstate, has come back to what it started from. And what we do is we carry out this integral, which is the integral as we go around the loop of the bra u times the lambda derivative of u, which is, these are two equivalent ways of writing this thing. This one just looks more symmetric and pretty. And this is a Berry phase that's only well-defined modulo 2 pi. And so why is that? Well, why is it indeterminate at all? The reason it's indeterminate at all is because I can't tell you with absolute knowledge what these states are. Let's say that they're the state of some molecule, the ground state of some molecule that I'm carrying around some path by moving an atom around a square or something. Well, the ket is only well defined up to a phase. I can multiply this ket by any phase, even the 5 pi over 7 or something like that, and it describes the same physical state, right? So a physical state really only corresponds to, the complex vector with an arbitrary phase. And so, for example, once I've defined one choice of functions, u as a function of lambda, I can define a new set, u tilde. This says e to the minus I beta of lambda times u. So beta is some real function that changes the phase of u. And when I do that and plug into this expression, the d by dk gets scrambled, and so the integrand changes. And so you would worry that the integral, which is phi that I'm trying to calculate, would also change. Well, it does and it doesn't. So here's what happens. First of all, when you go all the way around the loop, this u tilde has to be continuous at the final point. Right? So for example, if I start from 0, then u tilde and u are the same here. When I come all the way around, the u tilde and u have to be the same. So you would think that means that beta has to be 0. So this is a plot of beta versus lambda. You'd think that beta has to be 0 at the final point if it starts out 0 at the initial point. But that's not quite true. I could also have beta doing this, and now beta is 2 pi at the final point. And if beta is 2 pi, then e to the minus I 2 pi is 1, and that's also allowed. So it turns out that depending upon, so there's a kind of topology of what the, by the way, this is called a gauge change. So this e to the minus I beta of lambda, we call that a choice of gauge. In other words, the distinction between this u and the u tilde, these are two different choices of gauge. We use this word gauge in a way that's kind of analogous to the way it's used in electromagnetism. It's not exactly the same thing, but the idea is that when you make any physical prediction based on u or u tilde, you should get the same answer, but the intermediate results might look different. And that's similar to in electromagnetism where you choose the vector potential with different gauges. The intermediate results will look different, but any final physical predictions should be the same. Okay, so anyway, it turns out that the fact that this beta has to either comes back to itself or 2 pi up or 4 pi up, so by 2 pi times an integer, means that when I calculate phi tilde, it's going to be the same as the original phi plus 2 pi times the integer. And there's a quick proof here. I'm not really going to go through it, I think, for time, but you'll have the slides so you can look through it. Basically, the d by d lambda just acts in 2 places. It can act on the gauge piece, or it can act on the u. And the action on the u just returns the original phi, and the action on the gauge piece gives you this 2 pi n. So if you make any other choice of gauge as you go around this loop, you will either get exactly the same phase that you started with, or you'll get a phase that differs by 2 pi times an integer. So that means that they're all really the same thing. If I think of the phase as just telling me a point on the unit circle in the complex plane where this phase is located, then any choice of beta will give me the same point. And I really want to think of this point on the unit circle as the meaning of what the Berry phase is. Okay? So this is a little piece of mathematics. And there's a famous example of a Berry phase in the magnetism of a spinner. So if I have a spinner in a magnetic field, it has a spin-up state and a spin-down state. And if I follow the spin-down state as I change the direction of the magnetic field around some closed path, then this spinner has to change as I go around the closed path. And it turns out that the Berry phase, in this case, is just related to the solid angle that I subtend. It's actually just the solid angle divided by 2. So this is you sort of know about this in a sense, because if you take a spin up and rotate it all the way around to spin down and back up to spin up again, most people know from quantum mechanics that you pick up a phase of phi. And what you've really done is you've subtended a hemisphere which has a phase of 2 pi, and then in this case you divide by 2, so that's a phase of pi. Well, e to the I pi is minus 1, so you pick up a minus sign. So this is related to the fact that you have to do a 4 pi rotation of a spinner in order to come back to itself, including with the right sign. Okay, so here's sort of where we are. It turns out that you can write the polarization, again, I'm in one dimension, as the Berry phase as I take the block function around the Brillouin zone in one dimension times, well, over 2 pi to make it be an integer, times minus e, the charge of the electron, and that's what the polarization is in one dimension. In 3 dimensions, what I have to do is I have to say, well, let me calculate the polarization in the x direction. To do that, I'm going to average over strings of k points in the y and z direction, so I average over this kind of green plane, and at each point on that plane, I construct a string of k points going in the kx direction and calculate those Berry phases, and then I average them all. And this gives me the polarization. Okay, so maybe that's a place to stop and see, because I've done a lot of kind of formal stuff. If there's a question. I'll give you another chance at a question in a moment. Okay, let me just, so one of the first things that we did with this, again, we as a community, Resta did it first and we did it soon after. You probably know that the dynamical effective charge of an atom is defined as the first order change in polarization as you displace the atom. This is the same thing that tells you the infrared activity of a polar optical phonon. So you can do it by finite differences by displacing an atom a little bit and calculating the change in polarization. And in the perovskite ferroelectrics, there's an interesting story that came out in the mid-90s. You would guess that the titanium, let's say the titanium atom in barium titanate, I guess it's not labeled, but this is supposed to be barium titanate. This blue atom is a titanium atom. It's in the nominal 4+ charge state. So you'd think that if you displace that a little bit, it would induce a change in polarization, which is proportional to its +4 charge state, or maybe a little bit less because electrons screen. And the same with the barium is +2. So you might think that you'd get something like this, or numbers that are a little bit smaller. Instead, what you find is you get quite large numbers. We call these anomalous dynamical effective charges. So for example, when you move the titanium a little bit, it's as though you're displacing a charge of more like 7 rather than 4 quantum of charges. And well, it's a story I won't really go into here, but what happens is as you move this ion, the electron charge on the oxygen sort of shifts down in order to bond with it more strongly. And so it's a combination of the nuclear motion plus electrons moving in the opposite direction in response to a change in bonding, which gives these these large dynamical effective charges. Here's the oxygen in the apical direction. Instead of -2, it's like 3 times bigger. And then in the directions, the oxygen direction, in the other 2 directions, it's more of the nominal effective charge. Okay, so the summary so far, polarization can't be expressed in terms of the bulk charge density, but it can be expressed in terms of these funny Berry phases, where I have to go around the Brillouin zone, calculate derivatives with respect to wave vector, and integrate those up as I go around the Brillouin zone. And that gives me a practical way of computing the polarization. Now, most people find the Berry phases mysterious and counterintuitive, and there's an alternative view in terms of Wannier functions and Wannier centers that I want to present next. It turns out to be exactly equivalent to the theory in terms of the Berry phases, but I think it's a little more intuitive and tractable. Okay. So the Wannier center formulation. So again, I said that the block function is some envelope function times some underlying thing. And so this makes you think of waves and wave packets. And the question is, what is the most localized wave packet you can build out of these block states? And since the block states are actually periodic in reciprocal space, periodic in K, it means that the most localized object that you can make in real space is something that's like on the order of a lattice constant, a little bigger, but on that order. And those wave packets are called Wannier functions. So more precisely what we do is we start, so here again I'm making a kind of a toy model where I have an electron band, this is energy versus wave vector in one dimension. And let's say I look at one of the block functions, what I'm going to do first is I'm going to discretize this space into 6 points along the Brillouin zone. And then each one of these, I look at what the block function looks like. Now, the way you make a wave packet in real space is you take a linear superposition of states in k-space. And if you only take a small region of k-space, you get a very big Wannier function. But I want to get the smallest possible Wannier function. I want Wannier functions to be as localized as possible. And so what I want to do is use as much of k-space as I can use. And so what I do is I use all of it. So if I sum all of these 6 block functions and make a wave packet out of it, what it looks like is something that's relatively well localized in just one unit cell, in the home unit cell. So that's one function. But I had 6 block functions here. In order to have the same amount of information, I need to construct 6 Wannier functions. And what happens is that I can construct 5 more Wannier functions, like this one. The way I do it is I sum up all these block functions, but I put in an extra phase factor here, where this vector r is telling me how many unit cells I'm displaced from the origin. And so the basic idea is, think of it this way. These 6 block states are 6 states that span a certain Hilbert space, a certain subspace of all possible states. And these 6 Wannier functions are 6 functions that span exactly the same space. There's just a 6 by 6 unitary transformation that takes us back and forth between these and these. Really, that unitary transformation is just a Fourier transform. But I can use these Wannier functions just instead of the block functions to calculate whatever properties I want to. Energies, forces, whatever. It's a little tricky because these are no longer eigenstates of the Hamiltonian, because they're a mixture of Hamiltonian eigenstates. But anyway, they're still perfectly good functions. And for example, I can use the Wannier functions to calculate the expectation value of a position operator. So for example, if I focus on this red state, it's exponentially localized. And I can calculate the expectation value of the position operator in this Wannier state. Let's call this W0. That's basically what the next slide is. And here again, I'll go through this quickly. This is just kind of a sketch of the way the mathematics works here. Here's the Wannier function. It's an integral over the Brillouin zone of the block function. And I can write it as e to the a k dot r times the self-periodic part. And here's the trick. In order to write the position operator times this, I can rewrite it as minus I gradient of k with respect to this e to the I k dot r phase factor. Because after all this does is it pulls out an r, which is what I need on the left-hand side. So here this derivative only acts on the e to the I k dot r. And then I do an integration by parts. So going from here to here, I get a minus sign because I'm doing an integration by parts, and I move the derivative to act on the uk instead. So I get this. And then I take this ket W0, and I haven't done the algebra, but you can kind of see that the bra version of this will come in with 1 bra of uk, and you end up getting this expression. And that's the Berry phase. So basically what this says is that the expectation value of the position operator in the Wannier function is exactly the same as the Berry phase, except that the units are slightly different. So here's the more precise thing. You have some crystal. Here I've drawn the nuclear charges as these point positive charges. The electron charge is distributed quantum mechanically, but I can make out of the band, I can make a Wannier function, that's this blue thing. I can calculate the expectation value of the position of that Wannier function. And so, for example, that's right here is where the center of the Wannier function is. So that's the Wannier center. And then I can think of the crystal as composed, forget about the distributed charge. I can think of the crystal as just composed of these positive and negative point charges. And then the polarization that I want to compute is just the polarization of this toy model. So I basically reduce the real quantum mechanical charge distribution to these point charges located at the Wannier centers. And you can see now that the polarization has a kind of ambiguity in it, which is related to the fact that the Berry phase has a 2 pi ambiguity, because, well, I can say that the polarization of this unit cell points to the left because the positive charge is to the left of the negative charge, or I can take these two as my primary unit and say the polarization points to the right, and that's kind of a fundamental ambiguity that we can't get rid of. So there's a kind of what's called a branch choice of the polarization. As long as you're calculating changes of polarization, which is what we almost always do, we don't have to be a little bit careful about this branch choice, but it's not a problem in practice. Okay, so that's the Wannier center formulation. You might not think that's more intuitive, but I think it's a little more intuitive. Again, the idea from the band, from the blocked band, you make localized wave packets. It turns out that the center of that wave packet is well defined. I can think of the electron as being a point charge at that location, and then the the polarization of that lattice of positive and negative point charges is the correct polarization that I wanted to calculate. Let me just give you some references for all of this. There was a very nice review of modern physics early on by Resta, which explained all this. There are 2 book chapters that Resta and I wrote. The second one, I think you can download it directly from my website in the preprint form. This one you can request by email, since they're book chapters, they're otherwise not that easy to find. And I have a book that just came out last year, some of you may know, where basically chapter 4 is all about, well, chapter 3 is all about Berry phases, chapter 4 is all about electric polarization. So I go into all of this in much greater detail than I was able to do just now. So this is a good time to stop and ask for questions about this part, because I'm going to go to completely different things. Yeah?
I missed the point a little bit about the dynamical charges. So you mentioned it was one of the first. Just take the microphone, maybe it's better. Then everyone can hear the question. Yes, thank you.
I missed a bit why you mentioned those dynamical charges and what is their physical meaning.
Yeah, so you can think of the dynamical charges in either of 2 ways, well, let's say 3 ways. One is so let's say you have barium titanate and you want to talk about the dynamical charge of the titanium. If I take every titanium atom in the crystal and move them all up by, let's say, 1/10 of an angstrom, and you ask how much does that change the electric polarization, then the derivative of the polarization with respect to that displacement is the dynamical effective charge. Or if I take one titanium and move it alone by some small distance, what's the local electric dipole, which is locally induced? That turns out to be the same thing. And then by a kind of Maxwell relation, if I apply a uniform electric field inside the sample and ask for the force on the titanium atom, that also turns out to be the same thing. So it's any one of those 3 things, and it turns out it's the critical thing, for example, that determines the infrared activity, because if you have some oscillating mode, let's say you have titanium going to the right and oxygen going to the left, then the mode dynamical charge is the sum of the titanium one and the oxygen one with the appropriate signs, and that's the thing that tells you the oscillator strength for an infrared, infrared absorption measurement. Does that help?
Yes, thank you.
Okay. Yeah, question over here.
I might have missed this.
I think it's loud enough. Go ahead, just be loud.
What's the timeline between the Berry phase and the Wannier formulation? Like, were they around similar times? Or?
Yeah, so at least in the one-dimensional case, the connection, I think, was there from essentially the beginning. There was a subsequent development where we, this was with Marzari, some of you may know this, Marzari VanDerbilt. The question is, when you make Wannier functions in 3 dimensions, how can you make the most localized Wannier functions in 3 dimensions? And it turns out there you have to compromise between localizing in the x, y, and z in a complicated way. I think that was in the late 90s, 97 or something like that. But basically, the connection between the Berry phase and the Wannier center in one dimension was there essentially from the beginning. And I should say that this is all very close. I guess I mentioned Fowlis. I should mention him again. It's all very closely related to a theory of Fowlis about something called quantization of the charge transport. And so, you know, Fowlis actually, he was in a different kind of community. He wasn't in the computational electronic structure community. If I had walked into his office in 1993 and explained to him what we had just done, he would have said, "Oh, that's obvious," you know. But you know, in none of his papers did the word polarization appear because he was interested in other things, quantum Hall effect and that kind of thing. So, yeah, one more.
Yeah.
I guess
So it's very phase I've heard a lot. So what I understood, I just want to ask you if I understood correctly. So you mean that when the system is in initial state and it takes a like circular loop, it picks up a phase which has the contribution of time evolution and also the change in the eigenstate, and it changes, which also affects the Hamiltonian. So that is, this picked up phase is basically Berry phase, or how to physically think of it?
Well, let me try to make a slightly more precise statement. So we're always taking the wave vector k around a closed loop because that's the Brillouin zone. Then we have this other parameter, which is this adiabatic parameter that we're changing. And so mostly I talked about the case where we start from one configuration.
Maybe which other parameter are you talking about? See?
So
isn't this mysterious lambda parameter or some other parameter? What is it physically?
Let's be precise then. Suppose that I take all the titanium atoms in the crystal and I move all of them up and then to the right and then down and to the left. And in the process, lambda goes from 0 to a quarter to a half to 3/4 to 1. Right? So I'm going to go around a closed loop. If I only do the first leg, I go from here, from lambda equals 0 to lambda equals 0.25, then I'm not doing a closed loop in the parameter. I'm just making a finite difference of the parameter. And so that turns out that the change in polarization is the difference between the Berry phase calculated here and the Berry phase calculated here. If I go all the way around the loop, then the Berry phase at the end has to be the same as the Berry phase at the beginning. But if you actually follow what happens to the Berry phase, it can either, you know, as you follow the change, let's say it starts from 0, can go up a little, down a little, and come back to 0, or it can go up a little and end up at 2 pi. So in other words, if it changes by 2 pi, then what you've done is you've pumped one whole electron vertically from one unit cell to the next unit cell. That's the Fowlis adiabatic charge pump. And then what you've done is at the end, you've changed the polarization by one quantum, which is moving one electron by one unit cell. Okay, so that's the physical reason why there's this ambiguity in the quantum, is that you have the possibility of having this kind of charge pump loop. The only way that can happen is that in the parameter space, somewhere inside that loop, there's some metallic point or something going on where the band gap closes. That's a technical detail, perhaps.
It is a gauge transformation, is that correct?
A what?
A gauge transformation, so it has the same ambiguity as the vector, but then by analogy.
Well, yeah, I mean, so at a given structural configuration, the gauge ambiguity is only modulo 2 pi. If I then make small steps along this path, I can watch how this Berry phase changes, because I know it has to change continuously. And so if I go all the way around the path and watch how it changes, I can decide whether it came back to itself without any shift or a shift by 2 pi. If it has a shift by 2 pi, that's a physical thing. It's not just a gauge choice. It means that I have a configuration, I have a structural path in configuration space that physically pumped charge. So an example is, well, I don't have time to go into it carefully, but a sliding charge density wave. I can make a configuration I do it in the book. I can make a model of a sliding charge density wave where it's obvious that the electron is shifted by a lattice constant, but locally the Hamiltonian just comes back to itself. And so, so there are situations where you would have this ambiguity is really important, but in ordinary everyday calculations on perovskite ferroelectrics, you don't have to worry about this ambiguity modulo the quantum. Maybe one more in the back.
How does the theory deal with finite size systems, such as 4-unit cells, ferroelectric, and so forth?
So the question is about finite size systems. So, so basically, there you need to know about the connection to the surface. So there's an aspect of this that I didn't really describe, which is that you can prove a kind of theorem that tells you that if you know the in ordinary electrostatics courses, you learn that in connection with the polarization, there's a surface charge, which is given by the polarization dot the surface normal. So the correct version of that statement in this theory is that if you know the polarization in a bulk insulator, and if the surface is also insulating, and defect-free and ideal periodicity, then the surface charge is given by the bulk polarization modulo this quantum of uncertainty. In the bulk polarization, it corresponds to the uncertainty modulo 2 pi of the Berry phase, or of the choice of, in the Wannier function picture, it kind of corresponds to the choice of which atoms, which charges you pair up in the unit cell. At the surface, the ambiguity comes because you can add 1 charge per unit area, or subtract 1 charge per unit area by adding some alkali atoms, or if you have an electron band in the surface gap, you can occupy it or unoccupy it. And so this is what's known as the surface charge theorem. So for a finite system, what happens is if you change the polarization, you change the surface charge. If you then do everything self-consistently so that the electron charge generates potentials and feeds back, you get a complicated problem with a lot of screening you need to worry about. But yeah, I hope that answers more or less answers the question. Okay, so how far are we now? I'm going until 12:20. Okay, so let me start this next part. So using the standard methods of density functional theory, we can calculate energies of crystal structures. I just told you that we can also calculate polarizations now. And so, for example, for barium titanate, I can consider the pathway from the paraelectric state to the ferroelectric state with titanium up or titanium down, and generate this kind of picture, which is a double well potential, which is energy versus polarization. This is like an ingredient that you would use in a Landau theory of this material. So I can calculate the energy here, I can calculate the polarization is 0 here, I can calculate the polarization here. All of this calculation is at 0 temperature because when we do density functional theory calculations, they're implicitly always at 0 temperature. Now, as many of you may know, and I guess it was shown by Gustav, was it yesterday, there are interesting structural phase transitions that take place in the perovskite materials. And here in the case of barium titanate, when you start at high temperature and come down, so what this is a plot of the 3 lattice constants. So initially the 3 lattice constants are the same because the system is cubic at high temperature. And then it goes into a tetragonal phase where there are 2 lattice constants at the A and 1 lattice constant at the C. It gets a expansion in the vertical direction. And then it goes into an orthorhombic phase, and then finally at low temperature it goes into a rhombohedral phase. And the polarization here is 0, here it's along the 1 direction, here the polarization is 1, 1, and here the polarization is in the perfectly diagonal rhombohedral direction. And you see a little bit, well, this is a weakly first order transition. These 2 transitions, it turns out, have to be first order by this group-subgroup relation of symmetry theory. But in any case, the point is that there's interesting phase transitions as a function of temperature that we can't capture doing direct first principles calculations. Some of you might know that there's a method called first principles molecular dynamics or Karp-Paronella molecular dynamics, where you set up some big supercell and you set the atoms moving and you solve Newton's equations of motion using the forces calculated from density functional theory. That is just too expensive and too difficult to do on this class of systems, but that's not going to work. So I'm going to describe this effective Hamiltonian theory, which is basically developed by Karen Rabe and myself. Again, quite some time ago now. I guess maybe what are we around? 2000, I don't remember. 2005. So basically the idea is I want to choose a set of structural degrees of freedom that represent the possible low energy distortions, expand the energy, make a model in which I expand the energy in these variables with some parameters, fit the parameters to first principles calculations as far as possible with no experimental input. We sometimes cheat a little bit and use the experimentally known lattice constant. And then from that model, then we can calculate finite temperature properties like the sequence of structural phase transitions, dielectric and piezoelectric properties. People are now using this for the electrocaloric type of effect. So what are the low energy structural degrees of freedom in barium titanate? Well, you could guess this, but let me use this picture as a guide to determine this. What I'm showing is a kind of phonon band structure, but it has this funny stuff below the zero axis. And that's because what we're doing is the following thing. We're putting barium titanate in its cubic